Okay, Assalamualaikum warahmatullahi wabarakatuh. Today we will learn about properties of the definite integrals. In the previous meeting, we learned about definition of the definite integral and the fundamental theorem of the calculus. So today we will learn about the properties of the definite integral. In here, I want to show you that some properties in the definite integrals. And first, if we have the function f with the interval a comma b, and then for the function g is in the interval a until b, and then the two integral of the function, then the following properties that hold. And for the first, if the upper limit and lower limit of a definite integral are the same, then the integral is equal to 0. So in here, if we have the a from the lower limit and a from the upper limit from the function f(x) dx, so this is equal to 0. In here's the proof by using the definition of the definite integrals and then the fundamental of theorem of the calculus. We have to know that in lower limit is a and the upper limit is a, so the f(x) dx this is equal to f, and then this is we can change with a, right, minus f with the upper limit is a, so fa minus fa this is equal to 0. This is by using the fundamental of theorem of the calculus that we have learned before. So this is proof that we have the 0 in here. For the second is reversing the limit of integration change the sign of definite integrals. Let's see in here, if we have the integrals of f(x) dx from a until b, so this is equal to negative the integral of f(x) dx from the b until a. So in here we have the different upper limit and different lower limit. From the first we have the a as the lower limit, but in here we have the b as the lower limit, and in here we have the upper limit is b, and this is we have the upper limit is a. So if we have the different, or we can make a reversing the limit of the integration, so we can change the sign in here with the negative. So let's see the proof. In here we have the f(x) dx from a until b, so we have the fb minus fa, right? So we can get the negative in here, fa minus fb. This is equals to, in here, right? This is, we have the missing fb minus fa, fb minus fa. So it means that we have the same value, right, with negative fa minus fb, because this is same with this function. And then so it means that we have the fa minus fb, so it means that we have the b as the lower limit and a as the upper limit. So we have the negative in here, so we can change in and take in front of the integral. So it means that we have the same value. The definite integral of 1 is equal to the length of the interval of the integrals. Let's see in here, if we have the integrals of dx, this is only dx from the interval a until b, so this is equal to b minus a, right? In here's the proof. You can see in here's we have the 1 as the integrand of this function, so the integral of 1 is equal to x, right? As they use the basic integration formula you have learned before. So if we have the x, and then we can make the upper limit is b and the lower limit is a. So it means that we have the x, we can change with b, and then minus by using the fundamental theorem of the calculus, and then x with we can change with a. So it means that b minus a as this property. this is missing, b minus a, I mean. Let's go for the fourth property. A constant factor can be moved across the integral sign. For any c, and c this is a real number, and then we have the integrals of c times fx dx from the a until b. This is equal to c of the integrals of fx dx from a until b. In here we know that c is the real number, or we can say that it is constant factor. We have c, so this is equal. Let's see this proof. If we have the a until b from the function c times fx dx, so it means that we can use the fundamental theorem of the calculus we have learned before, so we can get the c in here, and fx dx is by the using the letter if v in here, we can change x with b or substitution b minus f with substitution a. So from here we can get the c, we can multiply c with fb and c with fa, so we can get the cfb minus cfa, and then we can make the c and c in here in front of in here, and then we have the fb minus fa. By using the fundamental theorem of calculus again, we can know that fb minus fa, so this is equal to fx, right? And the upper limit is b and the lower limit is a. So we can see this function, or we can say this, we can see this formula. So it means that we have the integrals of this is we have the a and this is we have b. So upper limit is b and the lower limit is a. And c of x we can change with c times fx ds because this is integrand. So this is the proof for number 4. Let's see for the next property. The definite integral of the sum and difference is equal to sum and difference of integral respectively. First in here we can see that if we have the function of x plus minus gx dx, and then we have the lower limit is a and the upper limit is b, this will be equal with the integrals of a until b of x dx plus minus the integrals of gx dx from a until b. So we can make it separately. The sum and difference of the integral is respectively, and then we can see this proof. If we have the fx dx in here with the upper limit b and the lower limit a, so we can use the fundamental theorem of the calculus. We can see that f b minus f with substitute a, and then we have the plus, and then we have the minus in here, and g in here we can change our substitute b, or by using the fundamental theorem of the calculus we have the gb minus ga. In here we can make if we have the b in here and a in here, b and a, so make it the same. In this function we have the fb, and we can make the gb in here take in front of in here, because this we have the same constanta. This is half b, on this have the same b, and this is b too. So fb times fb plus minus b, and then we have the negative in here. When we have the negative in here, so we can take a negative in here. If we have the fa like this and ga in here, but we can say, or we can take the plus minus in here, because in here we don't know this is positive or this is negative, so we can take in front of in here. So if we have to know this, we can make the f plus minus g, and then we have the value is b, and negative fa plus minus ga, so we can make the f plus minus g, and the value is a. from here we can get the integrals, right? From here we have b and we have a in here, so it means that we have the lower limit is a and the upper limit is b, and we have the fg in here and fg in here, so it means that we have the fx plus minus gx dx. Let's see for the sixth property. Suppose that a point C belongs to the interval AB, then the definite integral of the function f(x) over a and b, this is equal to sum of the integrals of AC and the psi b for any a, b, c is the members of the real number with a less than equal to b and less than equal to c. And you can see in here, if we have the fx dx from the interval a until c, this is equal with the integrals of fx dx from a until b, and then plus the integral of fx dx with the lower limit b until c. So let's see the proof. Before or with using the fundamental theorem of calculus, you have to know that if we have the a and then it is c, so it means that we have the fc minus fa, right? So from here we can make a manipulate of the proof. We have fc and fa in here is the same, so we can take fb minus fb, because fb minus fb this is equal to 0, so it means that it is not make the different value, but only we have the different form. We have fc minus fa, this is equal, and plus fb minus fb, because this is equal to 0, right? And then we know that if we have the fc, fa, fb, and the fb in here, so we can make the fb in here take in front of, and then we have the negative fa, we can take negative fa, and then we have the positive is fc, so we can get the fc in here and fb in here, so we have the fb minus fa plus fc minus fb. From here, by using the fundamental theorem of the calculus, we know that we have the limit is b, and then we have the lower limit is a, and we have the c in here and fb b in here, so it means that the proof of the property number 6 is correct. From the 7, this is we have the property if fx in here it is more than equal to gx for x the members of a until b, so we can get the interval of fx dx from a until b, it is more than or equal to the integral of gx dx from the interval a until b. So let's see the proof. The proof in here, we know that fx this is equal or more than equal to gx, right? So in here we can make the negative gx in here and negative gx in here, or we can use to reduce or more easier for minus by gx, this is minus by gx, so we can get the fx minus gx more than equal to 0, right? Or we can take gx in the other side, so we can get the fx minus gx more than equal to 0. So from here we can make or let fx minus gx as hx, and hx in here it is more than or equal to 0 for every x on the interval a until b. So we know that the integrals of a until b from hx dx is the area between the graph of ax and the x-axis, right? As they use the definition of the definite integrals we have learned before. So it means that hx this is more than or equal to 0. So if because this is more than equals to 0, so this property is proved, because fx dx and minus dx more than equal to 0. So from the 7 is proved. So, and then for the last property, if we have the absolute of fx dx from a until b, this will be less than equal to equal to the integrals of the absolute fx dx. We know that the a until b of x, this is the area between the graph of fx and the x-axis on the interval a. So we have the possible cases, and we have the two possible cases in here. Let's say for the case 1. In the case 1, if we have the fx, this is less than or equal to 0. For every x, this is the members of a until b. Or fx, it is more than or equal to 0 for x, this is members of a until b. Let's see in here, we have the opposite the figure. You can see in this print. Let's see this function fx. We have the below of the x-axis, right? So it means that the fx, this is less than or equal to 0. So we have the a, or we have the area, this is will be negative, right? If we're using the integral, so this is will be negative. Or we can know that this is we have the a in here as the negative. We have the a as the positive and negative a in here. And you must remember that if we have the absolute of a and make the absolute of a, this is will be same, right? Because the absolute will be positive, and this is always positive too. So it means that we have the integrals of a until b of x dx. Fx in here will be absolute because negative a and a, this is equal or same. So we can make the fx, this is always positive, or we can use them use the absolute in here. This is for the case 1. The case 1, if fx less than equals to 0. So let's see for the second, we have the fx more than equal to 0. So it means that the function is always positive, right? Because we have the absolute in here, and we know that the fx in front above of the x-axis. So what is the conclusion? The conclusion, it is only half of the proof. So we cannot make or justify the proof of the properties for this section. So we must make the case 2 in here. We have the cases 2. Let's see. C is the members of a and b. So in this fx, for example, in this, if fx less than or equal to 0 for x, the members of a and c, and then if we have the fx, it is more than or equal to 0 for x, the members of c until b. So we can get this function. We have the in fx, this is negative, and this is fx is positive because this is above of the x-axis, and we have the below of the x-axis. So in here we can make the integrals of a until b in here is a2, this is will be positive, right? And a1 will be negative because this is we have the below of the x-axis. And then so we can take the absolute in the both of side. This is we will be the absolute, and a2 minus a1 will be absolute too. However, so we can get the integrals of a until b, and this is the absolute of fx. Absolute of fx dx will be equals to a2 minus a1 with the absolute in here, right? This is will be fx, and then this is will be a2 minus a1, and this is will be positive. And then of course, if we have the absolute of a2 minus a1, this is will be less than equals to a2 plus a1, right? Because this is the difference, and this is the sum. Automatically, with the sum, this is will be more than equals the negative in here, right? So from this, by the triangle inequality, we can get the absolute of fx dx. It is will be less than equals to the integrals of the absolute f(x) dx from a until b. So in this section, let's see for